Good morning, everybody. Welcome to sunny Tuesday morning on Chem 1105 with your host, me, Dr. White. Hi, everybody. And let's go through what we'll be doing today. First, I have some announcements I want to talk about. Then we'll do the lab. Then I will do the review for test number 1. It's already the file, as I mentioned yesterday, is in Blackboard. And then after that, we'll go back to chapter 4 and work on that. So we got a busy day today. All right. One of the things I've done, and let's go to Blackboard, and I'm in student view. Yes, this morning I uploaded and sent as an assignment test number 1. Now, because this is a password protected file, notice what happens when I click on this. It asks for the password. You don't have that yet. Tomorrow, after class, I will send out roughly noon, give or take a little while. I will send out an email to each of you that will have the password to open up test number 1. Now, you probably got an email today from me, well, you should have, with the announcement that I sent out last week, but I took out the part which I got. You can't download test number 1 without the password, so you can't do it today. You'll have to wait till tomorrow. But when you do download test number 1, here's the periodic table you should use. I've included the instructions on how to make a PDF file with a cell phone if you don't have a scanner that does that. And if you want, I have information about Cam Scammer, which is, and use the free version, which allows you to do that super easy with your cell phone. I've never done it, but my students, many of them have, and they like it. Now, there was a misconception, mainly because of my doing. There's only one version of test number 1. And when you download it, if we're in a classroom, most of the students are done in 40 minutes. I would suggest take about 2 hours or so if you need it. You shouldn't. But if you do, there's no real time limit, except you need to have this uploaded by tomorrow. I think I have either noon or 1 p.m., somewhere around there, 1 p.m., and as a single PDF file. And as I mentioned, by Sunday or earlier, I will have your test scores in Blackboard, and I will send you an individual email, each student, with the points on each question. Next Monday, I will go through test number 1 answers in our Zoom meeting. I'll cut it out of the public video, but I'll create a private video that sometime Monday afternoon or Tuesday morning, I will send out a private email to each of you with the URL for that video. So if you can't make it to the lecture Zoom meeting, when I go over it next Monday, you'll still be able to see the answers. All right, before we move on, any questions about test number 1? All right, what I like to do, and I've changed how I did it in the past. I used to wait until the end to do the lab, but now I think it's better if I do that first, then we do the review, and then we do chapter 4 with remaining time. So without any other further notice, let's go to lab number 3. Let me remind you today, lab number 2 is due. Don't forget to include a selfie. I have ouch, a selfie with this piece or a piece of equipment, or you and the Alka-Seltzer tablets or whatever, or you'll get 0 points. Now, today's lab is measurement and certainty. And notice I have the ADA file, they call it, and then your lab report as a Word doc or a PDF file. And I always put in the instructions for how to upload it. All right, let's look at this PDF file about today's lab. Now, today's lab deals with measurements and uncertainty. What does that mean? Well, here they give you an overview. Students will use basic scientific measuring equipment to determine the accuracy and certainty associated with measurements using common laboratory glassware. Hang in there, I got to bring something over to my desk. I'm back. Profound. Duh. All right. First of all, let me remind you, for all our labs, even though today's lab, you're just dealing with water, you should wear your safety goggles. I have a different pair that I use that were given to me, all faculty get from COD, but the one in your set is quite good one. Now, equipment you'll need. You'll find a box like this that has a balance in it. Here's your balance. You have to put batteries, and they give you batteries in here. Now, to open the balance, just push up here, and here's your balance. Now, right here is an on key. And when you do this, it will be on a hard surface that's flat. And it takes a little while, a long while. And if you notice, it's bouncing around because I shouldn't be holding it. Now, there's a key here. You should press it so the letter G, I don't know if you can see it, the letter G right here is visible. The mode should be G. Now, over here is a button on the left, and it says tare. Tare is the chemist word, I don't know who came it up, for balance, to zero it. When you press the tare button, well, that's because I'm holding it like this, it zeros. If I were to put it down on my desk and press tare, it now says 0.00. Now, when you use your balance, you should write down all the numbers on the screen. This balance, and they're pretty accurate. I was surprised. I have a special weight set, was given to me as a gift, that you have in laboratories that use tweezers to put weights on a balance to check how accurate it is. And this is very accurate. Now, you'll be using this. I'm going to turn mine off now. You'll need your thermometer. And these are called, if you don't know, graduated cylinders. They're in your kit. In your kit, this is called an Erlenmeyer flask. And you'll need that. You'll need a couple of plastic cups and this plastic beaker. Now, moving things around, we're face to face in the lab. I have a big table where I work at in the front. All right, let's take a look at this. This is called a graduated cylinder. Think of it as like the measuring cup you have in your kitchen. It's a way of measuring volume of a liquid. And you pour it in here and you will see the level of the liquid come up. And if you look on this one, it has markings 6, 7, 1 through 10, 1 through 10. And then between each one, time out for my reading glasses. By the way, wow, it's been almost a year and 3 months ago, almost a year and a half ago, I had major cataract surgery. My eyesight is so much better. And anybody needing a great eye surgeon, he's in Hoffman Estates, Illinois. Excuse me. Email me and I'll give you Dr. Caven's contact information. Great, great eye surgeon. But now I need reading glasses. And there's 1, 2, 3, 4, 5 marks right here. Oops, guess what I don't have open? All right, now through this semester, I have to warn you, I'll be doing some artwork or drawing. My mother was a really great amateur artist. My father was a really great amateur wood carver. Guess what? Not one iota of their skills rubbed off on me. So when I draw something, don't laugh too hard and break a rib or hurt yourself. All right, let's look at a graduated cylinder, like I said, and you'll see markings here. Now, when you fill it with water, the water level will not be straight across. It's in what we call a U shape or meniscus. I hope I'm spelling meniscus right. So in here, the water will be U-shaped, and you measure the bottom of the U lining up to something. Now, if it's lining directly like this, so this line right here, the bottom of the U is lined there. So there's a line here that says 7. And each one of these in between is 0.2 milliliters. So notice this is 0.2, 0.4. If it's right on that line, I'm going to call 7.40 milliliters. And that's how you read a graduated cylinder. You look for the meniscus. Hold on. You look for the meniscus. It's a U. Which one does it line up? Let's focus. Doesn't want to. And Each one of these smaller ones is 0.2. Now, if it's anywhere between two lines, then that's 0.1. So if it's between 0.2 and 0.3, then I'd call it, say, 7.30. And you should be able to get three significant figures. Classes time. And if you look at the larger one, graduated cylinder, this says 40, this says 50. Each one of these is 1 milliliter. And if it was halfway between one of these, then that would be like 51.5. If it's right on the line, like right here, actually 40.15, it's right on this bottom line here, the U, not the top of the water, the U, then it'd be 41.0. And again, you should be able to get three significant figures. You have questions how to do this? See me, email me. You already know how to use the thermometer. Let me remind you, you do not have to shake this down. I put a paper towel, even though it does have this anti-roll piece on the thermometer. And similarly, this beaker has markings too. All right, let's get back to the lab. Now, here it tells you about the scale, how to put the batteries in, how to use it, how to make sure the mode is in G, how to tear it so it will be 0, and you'll be re-zeroing it. Now, when you measure a liquid, you'll pour it into graduated cylinder. You look at figure 1, they show you that meniscus, the U, and you read at the bottom. Now this one, I'm going to blow it up. Notice how this line, I would say, is touching. It's a little above, but let's call it touching. Here's 6, here's 7. So 6 at this line, 6 milliliters. Each one of these, now they have 10 here. Your small one doesn't. It's 0.2, but 5, 6, 7. So that each one of these on this graduated cylinder is 0.1. Now, assuming that U is right on the line, that would be 6.70. If it was in between the lines, I'd call it 6.75. And that way you can get three significant figures. Now, when you measure something, the accuracy of your measurement and the precision are important. Accuracy is how close the set of data is to the actual value. Precision refers to how close a data point is to other measurements. In other words, how reproducible. Now, today we're going to deal mainly with accuracy. And they talk about different types of errors. I'll let you read that on your own. And we have relative error. And here's a formula. The measurement, what would be the actual value, divided by that times 100. And the lower that number is, the more accurate your measurement is. And they've talked more about it and used that. They talk about a random error, which we're really not going to get into in this lab. And uncertainty is the limit of a quantifiable method with confidence using the measurement. You'll see something like this is accurate to plus or minus 0.1 or things like that. Now here they talk about how to read the meniscus. They call that 0.675. I said pretend it's on the line. If it was not on the line, this was what you would do. Now here they talk about measuring uncertainty with a low and high interval. And that's how you get on glassware. Now, don't forget, use significant figures. And they talk about how to do that. I've already taught you that. Now, I continue on significant figures and accuracy. All right, let's talk about today's actual lab. Here's the equipment I've already shown you will need. Now, I say a permanent marker, you can use your grease pencil. Remember, wear your safety goggles, and you should not eat or do anything while you're doing the lab. Now, determining the uncertainty in the lab balance. Turn your balance on, take 2 plastic cups, label them 1 and 2. And what you'll do is each time you'll press the tare button and put the cup on there. You'll do that for 1, you'll do that for 2. And you'll put that data in the mass, the grams. And remember, put all the numbers you see on the screen of your balance. And you'll repeat 3 and 4, take the weight of these a second time. And then you'll do 3 and 4 for 1 cup. You'll do 6 and 7 for the second cup, and you'll do it again. Now let's go to the lab report. So for the first part, cup 1, they have you do it 5 times. If you do it 3 times, that should be enough. And you'll do the same for the second one. And then you have a question 1 to answer. And it has, the dreaded words, please explain your answer. I don't expect a whole 2 pages of explanation, but a sentence or 2 should do that. All right, let's go to part 2. You'll need your graduated cylinder, both 1, 10, and 50. You'll need your Erlenmeyer flask and this beaker. Oh, by the way, for determining deviation for part 1, here's the formula you'll use. Now, in activity 2, you'll take your balance and place the 10 milliliter and remove the graduate. Let's see. Place the 10 milliliter on the balance and record the mass. Remove it, and then you'll put in water. By the way, the water for this lab, you can use regular tap water. The water for this lab, you can use regular tap water. If we were at COD, we have special filters for tap water that create what's called deionized water. But you don't have that in your home, and tap water will do the same. And then what you'll do is fill this to approximately 7 milliliters. Don't spend 20 minutes trying to get it 7.00. You'll be a little over. That's good. And what you'll do is record the water, volume of the water, based on your reading here. And then you should have somewhere here where you measure it. Here it is, an 8. You'll zero the balance and record the mass of the graduated cylinder and the water. Now you'll repeat steps 1 through 8 with this, your 50 milliliter, this, and you're going to have to guess because the only markers on here is 12.5 and 25. And same thing here, you'll need a different amount. Now, one thing I forgot to mention, in table 1 here, the amount of water you should put in the graduated 10 milliliters is about 7 milliliters. In the 50, about 24. In the Erlenmeyer, you're going to have to guess this, about halfway between 12.5 and 25 is about 17 milliliters. And the 250, the first reading is 35. So you got to guess about a little more than halfway between here and here and do that. Now, if we look at the lab, here we have the table. We look at the run for the 10 milliliter massive empty graduated cylinder. Estimated volume. Whatever you do, you read what you see in here. Higher volume, lower volume, like 7 and 8. Uncertainty. Mass of the glass and water. And mass of the water. Now, the mass of the water here is the mass of the glassware and water minus the empty glassware. Again, the mass of the water is the mass of the water and glassware minus that. And you do this for all these 4 devices. Now, in part table 3, let's go back to the lab, which is activity 3, you're going to record room temperature. And for this lab, you'll assume the water temperature is the same as the room temperature. Now, using the table below, record the density of the water at the current temperature of the room. How do we do that? Let's assume you take your thermometer, it's been out, laying on a countertop, and you look at it, and in my house, it's right now about 24.5. So what's the density of the water if I had been doing this? I look at 24, come over to the 0.5, and 0.9972. This is the density of water you would use. Now, for your room, it's going to be different depending on the temperature. Again, thermometer, you should be able to get 3 significant figures. Now, Notice here they have current temperature water and then density from that table. They have this blocked out, grayed out, because it's this number for all of these, this cut row, and it would be this number here. Now, what was the mass of the water that you determine by weight in activity 2? You put the numbers in for each graduated cylinder and Erlenmeyer beaker. And you have to calculate the volume of the water. How do you do that? And we're here. Where is it? It's got to be here somewhere. Volume equals the mass divided by the density. So to determine the volume of the water in, say, the 10 milliliter graduate, you take the mass and divide it by that number. In our case, in my room, it'd be 0.99, I think it was 27. And that will get you the volume when you use this density. Volume is the mass of the water for that measuring device divided by the density. All right. And then answer the questions here, 3, and that's it. So you actually only have 3 questions to answer and the data to put in. And that's today's lab. And what you'll find out is from the data you'll collect, which one of these devices or measuring glassware, it's actually plasticware. Nope, it's plasticware. In the lab, we would use glass, but it doesn't make a difference. Which one of these is the most accurate? And that's today's lab. Put everything away. Don't forget when you're through with your balance. Oh, by the way, since you're only using tap water, everything can go down the sink. And don't forget when you're done, turn off your balance. And put the cover right on. By the way, they really did give you a good balance. I was surprised how well of a job, what's the name of it, Carolina company did in developing the kit we're using. Last semester, for first time, we used the Carolina kit for Chem 1211, which is similar to this course. There are a few different labs, but a lot of them are the same. And I was surprised, one, how well it worked out for the students, and they liked doing them. And now, one thing, don't forget, include a selfie of you with any piece of equipment. I just dropped my graduated cylinder or with the balance. Either way, you only have to do one selfie. You can either embed it in your lab report or upload it as a separate file when you do the lab. This lab is due next Tuesday. Any questions? Aren't you glad I just don't say, read the lab and do it on your own? Boy, that lab work was thirsty work. All right, let's move on. What I like to do now is test number 1 review. And let me give the following caveat. I try very hard to put everything you should know for a test in the review. Once in a while, I might forget something. However, listen closely. If I've talked about something at least twice, even more times in the lecture, it's fair game on a test. Every question I have on my test, I've talked about the concept in the lecture at least twice, usually more times. Listen carefully. Anything we do in a lab will never be on my test if I haven't talked about it in the actual lecture. So anything we do in a lab, unless I talked about it in lecture and you did practice problems, hint, will not be on test. Now, this test number 1 review, if you go to Blackboard, click on course information, click on lectures, scroll way down, you'll see test number 1 review. And you can download this file. And that's what I'm going to be going through right now. All right, test number 1 review. First thing I talked about were the 4 branches of chemistry. And you should be able to name at least one of them. By the way, organic is the best, but I'm biased. I'm an organic chemist. There's also physical chemistry, analytical chemistry, and inorganic chemistry. I never liked inorganic of the 4 branches. It was hard. I wasn't good at it. I mean, I was good enough to get my PhD, but that's not my favorite branch. Next, I talked about matter. And you should know what is the definition of matter. It's anything that has mass and occupies space. At this time, I didn't include it here. You can look in the chapter 1 and chapter 2 lecture slides, chemical symbols. You should know the key elements, only 37. You should know if I give you the name, what's its symbol? If I give you the symbol, what's its name? And, oh, I don't have it open. Let me open it. All right, on your screen, this is the periodic table you will download for test number 1. Please don't go on the internet. I will know because certain ways I can tell if somebody has it. But you should know that if I say, what's the chemical symbol of lithium? It's Li. If I put down and test what element has a chemical symbol Li, you should know it's lithium. And you should be able to do that for any of the 37 elements I asked you to learn. All right, next we talked about, notice I say I talked about states of matter. The three states of matter you should know: solid, liquid, gas. You should know a solid has definite shape and definite volume. A liquid has indefinite shape, definite volume, and a gas has indefinite shape, indefinite volume. Now, when it comes to types of matter, there are different types. One is pure substances, and the two types of pure substances are elements, such as gold or mercury, or compounds such as water or salt, sodium chloride. Now, the other type of matter is a mixture. A mixture is when you combine two chemicals or substances and they each retain their own chemical identity. When we talk about mixtures, there's homogeneous and heterogeneous. If you mix two things together, like liquids, or a liquid and solid, or a liquid and gas, and once you mix it, if it's the same throughout, it's homogeneous. Same, same throughout. Heterogeneous, if you mix two things together and they separate, then that's heterogeneous. You should know what's an example of a homogeneous mixture. Well, if I take water and put sugar in there and shake it up, it will be the same throughout, homogeneous. I can do the same with salt. But if I take water and vegetable oil, vinaigrette dressing, and I mix it, it separates into two layers. Same thing, and do not try this at home. Do not try this at home. Gasoline and water are not soluble, and I'll teach you about what this meant, but they form two layers when you try and mix them together, and they form a heterogeneous mixture. Now, next I talked about properties of matter, two types, physical and chemical. And you should be able to give an example of a physical property, like my top is I don't know, I call it a gray color. You go out, look outside the parking lot, you'll be able to see red, blue, and green and other color cars. And then a chemical property, the ability of something to change. Gasoline is flammable. That's a chemical property. Water is not. Next, we talk about changes in matter. And there are two types, a physical change and a chemical change. Now, physical change is when you have a change in state. Example would be if I boiled water. When the water is boiling, you see it's going from a liquid to a gas phase. If you have in a liquid, if I were to put this in my freezer and come back tomorrow morning, I would see it's a solid, it's ice. That's how you make ice cubes, duh. But anyways, and the water is undergoing a physical change. Now, if I were to go out in a parking lot at COD, unfortunately, I'm sure I could find some cars with rust on it. And rust is when iron reacts with the air, oxygen, to form a new molecule called ferric oxide, which we call rust. That's a chemical change. Another example of a chemical change, and Dr. White loves candles, you should see my candle collection. When you burn a candle, the wax is melting. That's a physical change. but it's reacting with the heat and the oxygen in the air to burn to form a flame. And it's a chemical change. Let me get personal. In my stomach, and yours too, I don't know if I told you this, when I was about 2.5 years old, my mother said, don't forget to chew your food well before you swallow it or you'll choke. And guess what? I found out the hard way. She wasn't lying to me. She was telling me the truth. And I did choke on some food. I think it was French fries. I was just stuffing in my mouth, like a little kid, 3-year-old will do. And so when you chew your food before you swallow, and it goes in your stomach, it's broken down to other things. The food is undergoing a chemical change. Now, if I look at the clock, I think this would be a good time to come back in about 5-6 minutes, about 5 minutes, and we'll continue. So I'll see you in about 5 minutes. I can get up and stretch. Sorry, I got sidetracked. I'll be back in a minute and start. Sorry about that. That was a little longer than I expected. I got sidetracked. Sorry. All right, let's get back to the review. And we had talked about chemical changes. Let's talk about temperature. There's 3 scales: Fahrenheit, degrees F, Celsius, degrees C, and Kelvin. And you should know how to convert from one to the other. You use these formulas. Now, listen carefully. Common mistake is this one. You do the multiplication before you add 32. You do the multiplication before you do the addition. In the second one, you do the subtraction, degrees F minus 32, before you do the division. Again, you do the subtraction, degrees F minus 32, and then you divide by 1.8. You don't do each one of those separately, division, then the subtraction. That's wrong. Now, you've learned about significant figures. And let me remind you, on test 1, under your name, it will say print your name and sign it. Please do. Underneath, it will say, please use proper significant figures for all calculated answers. If you don't, if you put down all the numbers on your calculator, I'm going to take off a point. And if you do that 3 or 4 times, you lose points, and that won't help your grade. So use proper significant figures for all calculated answers. Now, I'll cover that in a little while in this review, but remember, in each of these formulas, the only thing that has significant figures is the temperature. 1.8 and 32 are exact numbers and do not play a role in significant figures of the answer. The reading, degrees C, how many significant figures that is, will tell you how many significant figures degrees F is. In the second formula, 32 and 1.8 are still exact numbers. Therefore, you should get the same number of significant figures, your answer, degrees C, as what was degrees F. And the last one, that's addition. Don't worry about significant figures. I'll teach you that later on. Next, I taught you scientific notation. Remember, scientific notation is a number Q times 10 to the n. This is important. That first number Q is number less than 1 or 10 or greater. You should know, and we went through this in the lecture and the problem set, go back and look at the videos, how to convert a number to scientific notation. I will not ask you, here's a number in scientific notation and write it in decimal. We don't do that anymore. Therefore, I'm not going to ask you that. Now, remember, if the number is greater than 10, then n up here is positive. If the number is less than 1, n is negative. And remember, you move the decimal to the right, either direction you're going, of the first non-zero number. And the number of moves is what n is. And if I were to write this in scientific notation, their word decimal would be here, 1, 2, 3, 4, 5. Trailing zeros with no decimal are dropped. This is 1.23 times 10. How many times did I move it? 1, 2, 3, 4, 5. This number, 123,000, is greater than 10. Therefore, this is positive in 5. Now, this number, to write it in scientific notation, move the decimal to the right of the first non-zero number. Lead zeros are dropped. But here's my decimal point. Zeros after the non-zero numbers, like here, are kept. And I moved that 1, 2, 3. This number is less than 1. It's negative, and that's how you do it. And I went through this. Now, next I talked about significant figures. All non-zero numbers are significant. Zeros may or may not be significant. Lead zeros at the beginning of a number are never significant. Now, continuing on, confined zeros, those between non-zero numbers, are significant. Trailing zeros, those at the end of a number, are significant if a decimal point is present in the number. Trailing zeros, those at the end of a number, are not significant if a number lacks an explicitly shown decimal point. You should know for test 1, if I give you a number, how many significant figures it has. And we went through that. Next, rounding off. The first digit to be deleted after the number of significant figures you want to keep is 4 or less. Simply drop that and all the following digits. If the first digit to be deleted is 5 or greater, then that digit and all that follow are dropped, and the last remaining digit is increased by 1. And if we look at this number, and you have to round it off to 3 sig figures for whatever reason, keep the 1, keep the 2, keep the 5. Look at that number. That's my first number after my 3 significant figures. And is that 4 or less or 5 or higher? 3, I hope you all agree, is 4 or less. You drop that and everything else. And the number is 1.25. And this one, you have to round off to 2 significant figures. How do you do that? Keep the 2, keep the 6. This is the number, my next number after my 2 significant figures I'm keeping. Is this 4 or less or 5 or higher? It's 5 or higher. So I'm going to drop these, increase this by 1, and this would be 2.7. And we went through things like that in lecture and the practice problem. And you should know how to do that. Now, we talk about operation rules. For this test, you just have to know the multiplication division rules. And that is, you got the same number of significant figures in your answer as the number you're multiplying or dividing that has the fewest significant figures. And you should know how to do this for test 1. Again, for multiplication division, you get the same number of significant figures in your answer as the number that you're multiplying and dividing that has the fewest significant figures. And if I were to have you do this calculation, what would be the answer using proper significant figures? You'll need your calculator. Make sure you clear it. Make sure you're in scientific notation. I showed you how to do that. Go back and look at the video where I did that. And I'll put in 2.867. Now I need to do 10 to the minus 5th. I'll do the blue key, second key. Then you'll see x to the minus 1, and above that is a double E. I'll press that. You should see an E on the screen. And I want 5, so I'll put 5. I'm going to multiply it. So I'll use this gray X. And now I have 3.1. And now I have exponential, again, 10 to what power? Second key, double E. And now I need a -2. Remember, use the negative in the bracket on the keypad for minus signs and an exponential. Don't use the subtraction key here. You need to use this one on the keypad. And I'll do -2, hit equal, and my calculator gives me this number. If you put that down, I'll take off a point, because this has 4 significant figures, all non-zero. And this has 2 significant figures. From now on, I'll abbreviate SF. So what's the lower number, 4 or 2? And hopefully pick 2. Therefore, this should have 2 significant figures. Well, it doesn't. I have to round off. I'll keep the 8, keep the 8. Next one I use to round off. Is that 4 or less or 5 or higher? Hopefully I'll pick 5 or higher. I'll drop that, increase that by 1. And this would be the correct answer. And you should know how to do that. And the same thing is true for division. I will not have addition on test number 1. You should know exact numbers, which we talked about in the temperature conversions, are not considered when determining the number of significant figures in a math operation. Let's continue. The periodic table. You should know the names of the different families. And those are alkali metals, alkaline earth metals, and I'll show you that in a second on the periodic table, the halogens and the noble gases. And you should also have a feeling for what elements are metals. Now, except for hydrogen, in this periodic table, in the column that has 1 above it, you should know that lithium, sodium, and potassium, those are the only ones I asked you to learn, are alkali metals. Lithium, sodium, potassium, alkali metals. In the second column with the number 2 above it, magnesium and calcium, those are the only ones I asked you to learn, even though Dr. White likes SR strontium, but you should know magnesium and calcium are alkaline earth metals. Magnesium, calcium, alkaline earth metals. We go over to column with the 7 above it, fluorine, chlorine, bromine, iodine, FClBri. Those are the halogens. What kind of gas is in the halogen lights, street lights? Halogens, either fluorine, chlorine, bromine, or iodine. And finally, in the last column, all the way to the right, with the number 8 above it, helium, neon, argon, krypton, xenon, you should know those are the noble gases. And on a test, if I ask you, give an example about the chemical name and the chemical symbol of a halogen, you could put bromine, Br. Of a noble gas, krypton, Kr. Of an alkaline earth, sodium, Na. Of a alkaline earth metal, magnesium. What would be an example of a metal? Iron, Fe. Copper, Cu. Ag, silver, Au, gold. Pt, platinum, and palladium, Pd, are also metals. All right, next I talked about the atom. You should know the atom is the smallest element of a particle, smallest particle of an element that retains all the characteristics of an element, but that's the smallest particle of an element. Next, very important, you should know the subatomic particles of an element atom are the electrons, protons, neutrons. You should know an electron has a negative charge, proton has a positive charge, neutron, no charge. Next, I talked about the nucleus of the atom. What's that? That's the center of the atom. And you should know it contains only protons and neutrons. The nucleus contains only protons and neutrons. And how do we find that out? Well, one of the things was Rutherford's gold foil experiment. And you should know that Rutherford's gold foil experiment helped elucidate, ooh, that's a fancy word, figure out that the nucleus of the atom, the center, contained protons and neutrons because it was very dense. Next, atomic number. On the periodic table, in our table, the upper right hand, you'll see a number. Like for, oh, my favorite element, carbon, you'll see the number 6, carbon chemical symbol C. And that means carbon has 6 electrons and 6 protons. By definition, the atomic number equals the number of protons of that element. And since all atoms have a net zero charge, that also means the atomic number tells you how many electrons in that element. And as I say here, you should know the atomic number gives you the number of protons in an element and the number of electrons in an element. And if I ask how many protons and electrons are in carbon, and as you just saw, the atomic number was 6, so that tells you have 6 protons, 6 electrons. Next, I talked about the electrons. Where are the electrons? In the center, the nucleus has the protons and neutrons. And all around it, in what we call the electron cloud, are the electrons. They're in shells, and each shell has subshells. And I'll mention this in a little while. And here the table shows you the shells have the name 1, 2, 3, and the number of subshells in each shell. 1 has 1 subshell, 2 has 2, 3 has 3, 4 has 4. And you should know that shell 1 is the lowest energy, shell 4 is the highest energy. And the same thing here. Subshell S is the lowest, and F is the highest. Excuse me. And here, we always fill the lowest shell and subshell. And remember, a subshell name is a number and a letter. A subshell name is a number and a letter. And the first subshell is 1s. Shell 1, and the subshell is, excuse me, hold on 1 second. I got to drink something, clear my throat. Test, 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 electron, test, test. It's back to normal. All right. Remember, a subshell is both a number and a letter. And here the maximum number of electrons you can put in each of the subshells. If I had 1s, 2s, or 3s, I can only put 2 electrons. If I have 2p or 3p, I can only put 6. Same thing for D and F. Now, you should know how to draw, write out, I don't know, I'm getting all choked up over this. You should know how to write the electron configuration, which is a statement of how many electrons an atom has in each of its subshells. And hint, that's numbers, letters. I did on the test. I've changed this to superscript numbers too. And yesterday, when wow, yesterday when I went through this, watched the video for chapter 3 problem set, I showed you how to do this. We did that in lecture 2. Next, let's talk about the valence electrons. You should know, what are the valence electrons? Those are the outermost electrons of an element. You should know, excuse me, I apologize. Something's in my, never mind, my throat is getting clogged up. But I can still breathe, good thing. You should know that the outermost electrons of an element are called the valence electrons. And how do you determine that? By looking at the top of the periodic table. And you should be able to, for this test 1, we're not doing Lewis structures, that's test 2, but for test 1, how many valence electrons does nitrogen have? Ooh, the chemical symbol N, look at the top, see the number 5, and the answer is 5. If I ask, how many valence electrons does calcium have? And you look at Ca, look at the top, and you see the number 2. So it has number 2 of it has 2 valence electrons. And with that, I'm done with the review for test number 1. And if you can, if you like what I did, this review, send me an email or give me a thumbs up. And I'd just like to get feedback. I hope you found that useful. By the way, good news, I'll be doing that for each test. And if you look at the syllabus, I also allot the week before the final about 4 to 6 hours of review, where I'll review the whole semester. Don't tell anybody I'm being nice. Shh. All right, any questions about test number 1? All right, well, in that case, let's go back to chapter 4. And we're talking about covalent bonding and how to draw the Lewis structure. And I just did hydrochloric acid. Let me do it again. And here we have hydrochloric acid, HCl. And Lewis structure means valence electrons. And each hydrogen has 1 valence electron. Each chlorine has 7 valence electrons. So if I draw the Lewis structure here, remember you put 1 dot on the side before you double up. And this hydrogen says to the chlorine, I've got an unpaired electron, valence electron. You do, let's share. And they do. And remember, a covalent bond is a sharing of 2 or a pair of electrons, one or more pairs, and that's a covalent bond. Now, yesterday, we started talking about bonded electrons. Those are pairs of valence electrons that are shared between atoms in a covalent bond. And non-bonding electrons. Those are pairs of electrons that are not shared or involved in the electron sharing. So if I were to ask you in a separate problem, in part A, circle the bonded electrons, 2 points, that would be these. If I had asked you in a problem in part A, circle the non-bonding electrons, and remember, they're always pairs, and in this molecule, those electrons are non meaning not, are the non-bonding electrons. And that's the skill, remember, this is all for test 2, not 1, that you should have. Now, let's have some fun and let's do some molecules and practice. Let's do chlorine. Chlorine, each chlorine, when we see the Lewis structure, that means you're dealing with valence electrons. So for chlorine, the first thing you have to do is say, well, how many valence electrons does a chlorine atom have? Good question. Thank you. And, oh, my throat's better. I better shut up. But anyways, chlorine, Cl, you look at the top of the periodic table and you see it number 7. It has 7 valence electrons. So if I take one chlorine and put 7 valence electrons, and I put a second one, and this chlorine says to that one, I've got an unpaired electron, you have an unpaired electron, let's share. And they do. So here are the shared pair of electrons now, but the non-bonding electrons are still there. And on a test, this would be your answer. Now this and this, you don't have to put down, but I'm showing you the mindset, how you get to the answer. Now, if we do it for water, hydrogen and oxygen, hydrogen has 1 valence electron. You can go and look at the periodic table. Oxygen has 6. Now, the only way to make this work for the Lewis structure is oxygen has to be in the center. And we have 2 hydrogens, 1 oxygen. And this hydrogen says, oh, oxygen, you have 1 unpaired electron, I have 1, let's share. And this other hydrogen says, oxygen, you have this unpaired electron, I have this, let's share. And they do. There's my shared oxygen, the other shared pair of electrons. And don't forget, the non-bonding electrons will still be there. Now, this NH3 is ammonia. And it's a very important molecule in our daily life. And I'll teach you later on when we get into reactions, talk about reactions, how the ability of chemists to create a method to make ammonia in a chemical plant back in about 1910, give or take a year or two, changed our planet. The ability to make this small molecule changed our planet in two different ways, one very good, one very bad. But that's life. And I'll talk about that later. But how do you draw the Lewis structure for ammonia? Now, ammonia has one nitrogen and three hydrogens. How many valence electrons does nitrogen have? If you look at the periodic table, you'll see it has 5 valence electrons. Hydrogen still only has 1. Now, to make this work, nitrogen has to be in the middle of those 3. How do we do that? Those are my 5 valence electrons. I have a hydrogen, that's 1. Remember, we have 3. A hydrogen here, 1 valence electron, and my third one. And this hydrogen says to nitrogen, hey, I've got an unshared, you got an unshared, let's pair. And this nitrogen says the same thing. I've got an unshared, you got an unshared nitrogen, let's share. And the third hydrogen says, I've got an electron, you've got an unpaired, let's share. And they do. I like that, and they do. So I have in the middle, my nitrogen, my non-bonding electrons are still there. This hydrogen, nitrogen share a pair of electrons. This nitrogen, this hydrogen, and the last one. If you notice, in ammonia, there's 1, 2, 3 pairs of shared electrons. Each one is a covalent bond. Those are the bonded electrons. So 1, 2, 3. In ammonia, there are 3 covalent bonds. And that's how you do Lewis structure for simple molecules like this. Now, you can have polyatomic ions, and I'm going to have to come back to this in a little while. We're going to skip this because I need to really talk about this first. Now, when it comes to life, I don't know if I told you this, you know who's the greatest of all chemists, or even more specifically, the greatest of all organic chemists? Mother Nature. And has she provided us some stuff to make covalent bonds fun? And she did. And it's time for Dr. White to get subtle. Hint, know this. Now, turns out you can have multiple covalent bonds. And there are 3 types of covalent bonds you should know. The first one is a single bond. And what is a single bond? A single bond is a bond in which 2 atoms share 1 pair of electrons. A double bond is a bond in which two atoms share two pairs of electrons. And finally, you should know there exists a triple bond. And a triple bond is a bond in which two atoms share three pairs of electrons. Now, you should know this, and I better. A single bond is one pair of electron, a double bond, two pairs, and triple bond, three pairs. You know baseball, when you hit a single, you go to first base, one pair of electrons. And if you hit a double, you go to second base. And a double bond has two pairs of electrons. And if you hit a triple, you go to third base, three. And a triple bond has three pairs of electrons. Now, if we were in face-to-face in a classroom, I would be saying to the whole class, all right, class, everybody together, let's say the three types of covalent bonds. The first one, single. The second one, double. And the third one, and the whole class would also say triple. At this point, because the first time we do this, they don't do it that loud. I said, oh, that was awful. We got to do this with some feeling. Fire up. This is exciting stuff. I'd say, fire up. What's the first type of covalent bond? And now everybody would yell out, single bond. I'd say, what's the second type? Everybody would yell out, double bond. And I'd say, what's the third type of covalent bond? Triple bond. And I thank the class because they just made me happy by getting all fired up. Now, you should know, single bond, one pair of electrons. Double bond, two pair. Triple bond, three pair. So there are the three types like I have here. Single bond, one pair electron being shared between two atoms. Double bond, two pair. Remember, a pair means two electrons. So one pair is two electrons, two pair, four electrons, three pair, six electrons total. But we usually use the term pair, but you should know that's two. And double bond, two pair of electrons being shared between two atoms. And a triple bond, three pair of electrons being shared. And let's do some practice. And let's do just two of these. Let's do nitrogen and oxygen, maybe a third one too. Now, one thing I neglected to mention, I better get back to HCl. Now, that's the octet rule. And I talked about it earlier, but I should have. And what that means is, and I'll never ask on a test, what's the octet rule? All atoms, when they share, lose, or gain electrons, they should have an octet, 8 valence electrons. That's total of shared and bonded and non-bonding electrons. There's one exception. Hydrogen's octet is 2. So every element, when it's in a covalent bond in a molecule, should have an octet, except hydrogen's octet is 2. So if we look at HCl, hydrogen has 2 valence electrons. Its octet, remember, is 2. But if we look at the chlorine here, how many dots do you see in that blue circle? 2, 4, 6, 8. An octet. Let's do this again for water. Now, if we do again in red, each hydrogen, that's the number of bonded and non-bonding electrons it has, and that's 2. And remember, the octet for hydrogen is 2. Now, if we look at oxygen, it should have 8 bonded and non-bonding electrons. If we look in the blue circle, 2, 4, 6, 8, octet. You could also 2, 4, 6, 8. Who do we appreciate? Dr. White? And never mind. Oh, it's bad humor slipped out Tuesday. So remember the octet rule. All right, let's go back. Remember, 1 pair electron being shared, single bond. 2 pair, double bond. 3 pair, triple bond. And, whoops. And let's do the for nitrogen gas. Now, if you look up on the periodic table, let's do that. You have to find, when you're doing Lewis structures, how many valence electrons does an element have? If we look here, we have nitrogen, not this number. Look at the top, has 5 valence electrons. So I draw 1 nitrogen. Remember, a dot on each side before you double up. An organic chemist always put the non-bonding pair of nitrogen on top. You don't have to, but I am an organic chemist, and we do that. I don't know why, but and here's the second nitrogen. Why? Because it's N2. And this nitrogen says, oh, look, I have 1, 2, 3 single electron, valence electrons. You have 1, 2, 3 single electrons. Let's share. And they do. The non-bonding electrons stay there. So how many pairs did we have? 1, 2, 3. Same here, 1, 2, 3. And therefore, I'll have 3 pairs of electrons. And what is 3 pairs of electrons? Oh, look, somebody was nice enough to write a table here. And that's called a triple bond. And here we have nitrogen. We have a triple bond there. So nitrogen makes up about 80% of the air you're inhaling right now. And guess what you can do? Next time you're with some friends and you see one of them breathing, hopefully they all are, you can sell them, say if you're at lunch, dinner, breakfast, or at a party, you know, the air you're breathing has nitrogen gas N2, and it's got a triple bond. Friends don't like to hear that. Restaurants or at parties or just getting along with each other, getting together. But when you inhale, you're taking a nitrogen that has a triple bond. Now, if we look at another one, let's do the other part of air, oxygen. And the oxygen in the air keeps you alive. That's a good thing. Now, I'm going to go a little later. Normally, we take a break now. I'll go for a little while, and then we'll end early. Because actually, I'm ahead of schedule a little, which is a good thing. All right, so if the question is draw the Lewis structure for oxygen gas, O2, this is oxygen gas. How do you do that? Well, you have to first of all find out how many valence electrons does oxygen have? And the answer is not the atomic number. Look at top and you see the number 6. So oxygen has oxygen atom, 6 valence electrons. And oxygen gas, there are 2 of them. So I have one oxygen with 6 and a second one with 6 valence electrons. And this oxygen says to this one, I have 1, 2 unshared valence electrons. And you have 1, 2 unshared valence electrons. Let's share them. And they do. Now you have 2 oxygens, and they still have, each one has 2 pair of non-bonding electrons. But now we have 1, 2, 1, 2. 2 pairs of electrons being shared. Now, the one thing I'll go back, I forgot to, bad Dr. White, and that is the octet rule. But first of all, what kind of bond is between oxygen atoms and oxygen gas? Well, 2 pair of electrons. Oh, look, someone put a nice table up here. 2 pair of electrons is a double bond. Therefore, this is a double bond. And the next time you're with some friends and you see somebody inhaling air, you could tell them, you know, the oxygen, the air you just, oxygen gas in the air you just inhale has a double covalent bond. Nah, don't do that. Friends don't like to hear that unless they're chemists. Even then they'll look like, yeah, I know that. But it's true. Now, the one thing I forgot to point out is the octet rule. In covalent bonds, elements share electrons to get 8 valence electrons, octet. The exception is hydrogen. But if we look here, that's both shared and non-bonded and non-bonding electrons. 2, 4, 6, 8. This nitrogen has a total of 8 valence electrons, its own and shared. If we look at this nitrogen, it has 2, 4, 6, 8, both shared and non-shared pairs, non-bonded and bonded pairs of electrons. So both of those have the octet rule. If we look at this molecule, oxygen gas, this oxygen here has 2, 4 non-bonding electrons plus 2, 4 bonded. That adds up to 8. It has 8 valence electrons, shared and unshared. If we look at the other, that has 8 valence electrons. So it's happy. Oh, let's do one more before we call it a day. What would that be? Now, let's look at carbon dioxide. Carbon dioxide is the gas you exhale from your body. It's a way of your body getting rid of carbon waste. Also, when you burp, most of that is carbon dioxide. Now, if you have a can or bottle of what we call in the Midwest, Chicagoland pop, by the way, Dr. White loves Dr. Pepper and Burners. If you don't know what Burners is, oh, are you missing stuff? You can buy it at Jewel. I don't get any kickback, but it's a very highly carbonated, spicy ginger ale. I've been drinking it for years. I love it. Dr. Pepper too. And if you look at the bottle, when you open it and pour it in a glass, you'll see the little bubbles. We call that carbonation. That's CO2, carbon dioxide. And if we look at carbon dioxide, and you have to write the Lewis structure for CO2, we have 1 carbon and 2 oxygens. How do we know that? And if I look up on the periodic table, which I will do, carbon has 4 valence electrons, oxygen has 6. So carbon has 4 valence electrons, oxygen has 6. The only way to make this work is carbon has to be in the center, and on each side you have an oxygen. What I just did is draw the Lewis structures for each one. Now, carbon says, oh, to this oxygen, you have 2 non-bonding electron or single electrons. I have 2. Let's share. And the carbon says to this oxygen, you have 1, 2 unbonded electrons or an single pair of valence electrons. I have 1, 2. Let's share. So this oxygen and this carbon shares 2 pair of electrons. This oxygen still has its non-bonding electron. And then the other oxygen has 1, 2, and this has 1, 2. And they share. So 2 pair of electrons being shared, and the non-bonding electrons on oxygen are there. And what kind of bond is between this oxygen, this carbon? Well, two pair of electrons. We go up here, that's a double bond. And we look here, same thing. Two pair of electrons, double bond. And now we have to check the octet rule. You don't have to do this on a test, but it's a good check to see if you did it right. So if we look at this oxygen, it's got two pair of non-bonding electrons, two pair of bonded electrons in the red circle, 2, 4, 6, 8. If we look at this oxygen, how many non-bonding electrons does it have? 2, 4, 6, 8. It's good, octet rule. Now let's look at the carbon. How many bonded and non-bonding electrons? Well, it doesn't have any non-bonding, but it has 2, 4, 6, 8. Count the dots in the blue circle. It's got an octet. So the next time you're with a friend, and you see them drinking pop, and you can tell them, you know, the bubbles in there, that's carbon dioxide, and it has two double bonds in it. Nah, don't, but you can still think about it. So as I look at the time, I think I'm going to end a little early because we're ahead of the schedule, which is a good thing. So with that, don't forget there's a lab due today. We did last week. Don't forget, tomorrow, I will send out about noon or maybe even a couple minutes earlier, but around that time, an email to each of you. It will have the password for the password protected PDF file. Once you get that password, you can open it up and download it, and you'll take test number 1. You'll have until tomorrow, till Thursday, 1 p.m. to take test number 1 and upload it as a single PDF file. And it should only take you about 40 minutes, but if you need more time, like 2 hours, you can. That doesn't include making a PDF file of your answers and uploading it. If you do not have a printer like I have, that's a nice black laser jet printer. I don't buy the colored one. I don't need them. And they're easier to keep running. Then just write the answers on a piece of paper. You do not have to write the questions. Make your life easier, and you can make that with your cell phone into PDF file if you don't have a scanner, and upload it. And with that, I'm done. Gang gesund. Goodbye. I stole that from Granny to Beverly Hillbillies. Gang gesund. Goodbye now.